Let me actually remember to call IT about that. Hopefully they'll have it fixed by tomorrow. Okay. Now on this one, you could make your u equal x squared, but if you're going by, and I'll show you later why you wouldn't want to make it equal x squared, because it would actually cause you to have to repeat the process over and over. Okay. So remember, you have a logarithmic function, so you want to make that your u. So u equals natural log of x, which means your dv would be x squared dx. Like I said, you wouldn't be wrong if you picked u as your x squared. It would just be a little more work. Okay, so we have your u, we have our dv, our du is equal to 1 over x dx, and our v, which is just the integral of dv, is the integral of x squared dx. Okay, so we know that v is equal to 1/3 x cubed. Okay, so we have our u, our du, our v, and our dv. Okay, so we're all set to just plug everything in. Okay, so the integral of u dv equals uv minus the integral of v du. Okay, so that's going to equal uv is natural log of x times 1/3 x cubed. So you can make that 1/3 x cubed natural log of x minus the integral of v, 1/3 x cubed, du, which is 1 over x dx. There we go. Okay, so that's going to equal, we still have our 1/3 natural log of, well, 1/3 x to the third natural log of x minus, we can get that 1/3 and factor it out, and this actually becomes 1 squared once you cancel one of the x's out. Okay, so this becomes 1/3, bring that up a little bit, x to the third natural log of x minus 1/3, oh, clean that up a little, 1/3 x cubed over here, once we solve for the integral of x squared, plus c. Okay, now we just go ahead and combine our 1/3 x cubed natural log of x minus 1/9 x third plus c. All right, and that would be your answer. All right, any questions on that one? All right. Yes.
There's a integration by parts video that I watched where it had you set up like a table of views and DVs.
Yep, you're talking about the something method. Can't think of the name of it. Nope, not on this one. I mean, you can later, but you have to actually use integration
Or
by
like a
parts.
cell
Yeah.
method or whatnot.
Oh, and DiffEq, I use that all the time.
Right.
It's so much faster.
Right, okay,
Yeah.
I was just wondering.
Yep, but it actually does work. All right, so I think it's called either I know Kroneker's method is one way it's called, and cannot think of the other name of it. Tabular method.
Tabular,
That's
okay.
it. Tabular method. So even though tabular method does work, you can't use it in place of integration by parts. So, at least not yet. All right, so say for example, if you wanted to evaluate the integral of 14x cosine of x with respect to x, using integration by parts. Okay. Now with this one, you could factor out the 14 if you wanted to, but a lot of times it's easier just to have the 14 as part of it. Less likely to forget about it. Okay, so we'll let u equal 14x, and dv equal cosine of x dx. Okay, because remember, algebraic comes before trig function in our LIATE acronym. Okay, so that means our du is going to equal 14x dx. And our v is going to equal the integral of dv, which is equal to the integral of cosine of x dx. Okay. So our v is equal to sine x. Okay, we have our u, du, v, dv, so now we just plug it in. Integral of u dv equals uv minus the integral of v du. Okay, so that's going to equal uv, which is 14x times sine x, minus the integral of v du, which is 14 dx. Okay, so now we just go ahead and factor that out. So you have 14x sine of x minus 14 times the integral of sine of x dx. Okay, so that becomes, bring that up some, 14 sine of x plus 14 cosine of x plus c. All right. So any questions on that one? All right. Oop, anyone's still writing? Okay. And make sure to continue. All right, so let's say, for example, what if you wanted to find the integral of 3x cosine of x dx? Okay, And I'll let you try that one first. Yes.
Quick question.
Mhm.
Does it work for definite intervals as well, right?
Oh, yeah.
If I got another day, how to do that?
Oh, yeah, with definite intervals, really all you do is once you solve it, just plug the values in. Let me see, do I have one? I'm going to try to get to those, hopefully. Yes.
Are you gonna end up the exams today?
Yep, actually I am. I left them in the other office. Oh, in my office, so I'll hop back and grab those before the end of class. All right, so for this one, using our LATE, algebraic term comes before trig, so let u equal 3x. And our dv equals cosine of x. Which means our du is equal to 3 dx. And our v, which is equal to the integral of dv, which is the integral of cosine of x dx. Okay, so we know our v is equal to sine of x. Okay, so now we just go ahead and plug it in. The integral of u dv equals uv minus the integral of v du. Okay, so it's uv, so 3x sine x, minus the integral of v, which is sine of x, du, which is 3 dx. We can just get the 3 and bring it right on out to the front. Integral of sine of x is negative cosine. So that's the 3x sine of x minus 3 negative cosine of x plus c. Okay, so this actually just becomes 3x sine of x plus 3 cosine of x plus c. Bring that up some. All right, so any questions on that one? All right. Make sure everyone's done. All right, so let's say if we use the other example. Say if we want to find the integral of 4 natural log of x over x cubed dx using integration by parts. Alright, so for this one, you might want to rewrite it first. So you have 4 natural log of x, x cubed dx. You can actually just make it the integral of 4 natural log of x times x to the negative 3 dx. Okay, so remember, using your LIATE acronym, logarithmic function comes before algebraic, so you're going to make your u equal natural log of x. Okay, so just to put it in order, say natural log of x, 4x to the negative 3 dx. That's your u, and that's your dv. Okay, so we know if our u is natural log of x, and our dv is 4x to the negative 3 dx, our du is going to be 1 over x dx. And we have our dv, and our v is just the integral of dv. Which is the integral, and might as well put the 4 on the outside, x to the negative 3 dx. Okay, so that's x to the negative 2 over negative 2. So that means our v is equal to negative 2 x to the negative 2. Okay, so now we have everything. We just go ahead and plug them right in. Bring that up a little. The integral of u dv equals uv minus the integral of v du. Okay, so our uv is natural log of x and negative 2x to the negative 2. negative 2x to the negative 2 natural log of x minus the integral of v, which is negative 2x to the negative 2 du, which is 1 over x dx. Okay, so if we go ahead and combine those two, we end up with, you might as well say plus 2 times the integral of x to the negative 3 dx. Okay, so negative 2x to negative 2, natural log of x. So you have x to the negative 2 over negative 2. So you end up with negative, you might as well say negative 1. X to the negative 2 plus c. Okay. Or if you wanted to, you can just put all of the negatives in the denominator. Okay, so negative 2, oh, move that up some. Natural log of x over x squared minus 1 over x squared plus c. Okay, any questions on that one? Yes.
When you integrated the two integral of x to the negative third,
Mhm.
isn't just like it would be 2 times like negative 2x to the negative 2 power, so wouldn't it end up being negative 4x to the negative 2 power?
Nope.
The 2's wouldn't cancel.
Well, with that one, remember it's x to the n plus 1 over n plus 1.
Right.
So that would be to the negative 3 plus 1, which is negative 2
Right.
over negative 2.
Over negative.
Yep, so those two would cancel out.
Okay, that's right. Okay.
Okay. Any other questions on this one? All right. So these were the fairly, I guess you could say, straightforward ones. They can get a little bit tricky. Sometimes they'll come from a simple integration and have a really long actual solution. All right, anyone still writing? All right. Okay, so let's say if we decided to evaluate the integral of sine inverse, not secant inverse, x dx using integration by parts. Okay. Now for a problem like this, you only have one factor. Okay. So we'll let u equal sine inverse of x. But we can let our dv equal dx. Okay. Which means our du is equal to 1 over square root of 1 minus x squared dx. And our v, which is the integral of dv, which is just the integral of dx, our v is equal to x. So we have our v, our dv, our u, and our du. Okay. So now we just go ahead and plug it in just like we did before. Okay, the integral of u dv equals uv minus the integral of v du. Okay, so uv, just sine inverse of x, minus the integral of v du. I guess I'll put it that way. Okay. Now, if you wanted to, you could just make it x over square root of 1 minus x squared. Okay. Now this one you can just solve using u substitution. So make a little side note for that one. Okay. What if we let u equal 1 minus x squared? And our du is equal to negative 2x dx. So du over negative 2 equals x dx. Okay, so if we might as well put the dx up top, make it all look nice and neat. Then that's going to equal, move that up a little, x sine inverse of x minus du, the integral of du over negative 2 times square root of u. Okay, so once we factor out that negative 1/2, it becomes plus 1/2 times the integral u to the negative 1/2 du. Okay, so it ends up being u to the 1/2 over 1/2, and those two 1/2s will cancel out. U to the 1/2 plus c. Now we just plug back in our u. This is x sine inverse of x plus our u is square root of 1 minus x squared.
That would just be 1 minus x squared, because you left the square root in.
Oh no, that's because before it was negative u to the 1/2. But then when you add 1, it became positive.
The one that separated you.
Hmm? Which one?
U is just 1 minus x squared.
Yeah, it's not the square
Yeah.
root of that.
Yep, but you already had the square root there. So once you plug in that one there, it becomes square
Sorry, I
root.
was just-
Oh, I know, it's real easy to miss. Square root of 1 minus x squared. And just because of that there. Plus c. All right, and that's your answer. Okay. Any questions on this one? All right. Oh, anyone's still writing. All right. So this one is actually one of the types that can get a little lengthy. Okay, so let's say,
Your time's gonna run out.
oh, thank you. Might as well